Hello everyone, welcome back. The topic in this video is the Euclidean algorithm. This is an algorithm to find the GCD of two integers. Here we'll be talking about finding the GCD of the integers a and b. And first of all, I'm going to start with two facts here. So let's let a, b, and r and k be integers, and let a be equal to bq plus r, and this is by you can think of this by the division algorithm. So if you divide a by b, q is the quotient, r is the remainder. Now if k is a divisor of any two of the three numbers a, b, r, then k is also a divisor of the third number. So in other words, what I'm saying here is that if k divides a and b, then k also divides b and r. Or you can say if k divides r and a, then k divides b as well. So if k divides any two of the three numbers a, b, r, then it divides the third. Another fact is that if you have the equation a is equal to bq plus r, then the GCD of a and b is the same as the GCD of b and r. Now the good thing about this, the implication of this theorem is that you see, if you start with a and b, and you're trying to find, let's say b is less than a, you're trying to find the GCD of a and b. Now, because the GCD of a and b is the same as the GCD of b and r, so you just have reduced the size of your problem because r is less than b. So if you started with the pair, if you wanted to find the GCD of a and b, you can find that by just finding the GCD of b and r. And the size of b and r would be less than the size of a and b. Now these two facts follow by just looking at the equations. A is equal to bq plus r, which is the same as r is equal to a minus bq. So notice that so why would they why is it that well, first of all, let's look at the first theorem here. So if you say that k divides, so notice that if you look at the first equation, if k divides b and r, then then k divides the right hand side, and then k divides a. So if k divides b and r, then k must divide a. Now if you look at the second equation, if k divides a and b, then k must divide r. So now notice that if k divides a and b, right? If k divides a and b, any common divisor of a and b will also be a divisor of r. So and any common divisor of b and r will be a divisor of a as well. So that tells you that the GCD of a and b and GCD of b and r would be the same. So we're going to make use of this in the Euclidean algorithm. So let's say we want to find the GCD of two integers a and b, and I'm going to label them as r0 and r1. The next step would be that we divide r0 by r1 by using the division algorithm. So r0 would be r1 times the quotient q1 plus the remainder r2. Obviously r2 is strictly less than r1. Now we divide r1 by r2, and if I divide r1 by r2, then I'm going to get a quotient q2 and the remainder r3, and r3 is strictly less than r2. And if we keep going like this, and then at some point, let's say on the kth step, rk minus 1 would be rk times qk plus rk plus 1. And let's assume that, see the values of these r's, right, r1, r2, r3, and so on, these are non-negative integers and they are strictly decreasing. So at some point, rk plus 1 must become 0. So at some point, so let's say rk plus 1, 0, and then what happens is that you can say that rk is the GCD of A and B. So why is that the case? Well, if rk plus 1 is 0, then what is the GCD of rk? See, the GCD of rk and rk plus 1. Well, if rk plus 1 is 0, the GCD of rk and rk plus 1 would be rk. But the GCD of rk and rk plus 1 is the same as the GCD of rk and rk minus 1. So the GCD of these two and the GCD of these two are the same. So you can say that the GCD of rk minus 1 and rk would be rk. And then you go backward, and in each of the steps backward, you'll see that rk would be the GCD. So so if you say that R2 and R3, the GCD is RK, then the GCD of R1 and R2 would be RK. And then if the GCD of R1 and R2 is RK, then the GCD of R0 and R1 would be RK. And so that's what you wanted to find. So the point is, if we keep using the division algorithm like this, as soon as we got the remainder 0, the previous non-zero remainder would be the GCD. So let me explain that in an example now. Let's say I want to find the GCD of 24 and 18. I start with 24. So you divide 24 by 18. Then you get a quotient 1 and a remainder 6. Okay, so now we divide 18 by the new remainder 6. So we get 18 is equal to 6 times 3 plus 0. So we got a remainder 0 already, so we stop. And the GCD would be the previous remainder that we got, which is 6. So the reason is, again, if you look at the second equation, the GCD of 6 and 0 is 6. But the GCD of 6 and 0 is the same as the GCD of 6 and 18. So the GCD of 6 and 18 would be 6. Now GCD of 6 and 18 is 6, so then GCD of 18 and 24 would be also 6. Okay, so that's how we get this GCD 6. Here's another example. Let's say I want to find the GCD of 162 and 31. So I start with dividing 162 by 31, and that's going to give me a remainder 7. And then I divide 31 by 7, that gives me a remainder of 3. And then I divide 7 by 3, that's going to give me a remainder of 1. And then I divide 3 by remainder 1, and that's going to give me a remainder of 0. So once I get the remainder 0, then I stop, and the previous remainder is my GCD. The reason is the following. So if I say that the GCD so the last equation tells me that the GCD of 3 and GCD of 1 and 0 is 1, but the GCD of 1 and 0 is the same as the GCD of 1 and 3, so that's 1. GCD of 1 and 3 is 1, so GCD of 3 and 7 would be 1. GCD of 3 and 7 is 1, so GCD of 7 and 31 would be 1. GCD of 7 and 31 is 1, so the GCD of 31 and 162 would be 1. So that's how we get 1. So basically we are applying this second theorem here repeatedly to get to the GCD. Okay, so here are some exercises that you should go over before you move on to the next slides. And the next video will be going over the extended Euclidean algorithm. See you then.